The true frontier of AI isn't predicting a label. It's mastering control in chaotic dynamic environments, where a single optimal action is elusive and an explicit model of the world remains unknown. This is where policy gradient methods in reinforcement learning redefine the game. Instead of meticulously calculating the value of every possible state-action pair, they directly optimize the policy, the agent's behavior strategy itself. Imagine an agent learning to navigate. Policy gradients adjust the probabilities of taking specific actions from given states. If an action leads to a high reward, its probability is increased. If it leads to a penalty, its likelihood decreases. This is achieved through gradient ascent, pushing the policy towards trajectories that maximize cumulative returns. We're not estimating Q values, we're directly shaping the decision-making function. Consider robot manipulation, learning intricate tasks like grasping irregularly shaped objects or assembling components in a factory. Here, the action space isn't discrete buttons, it's continuous joint angles and forces. Policy gradient approaches, like actor-critic architectures, shine, enabling smooth, nuanced control that value-based methods struggle to represent. Think real-time dynamic balancing or dexterous manipulation. Contrast this with Q-learning's reliance on a Q-table or a deep Q network to approximate action values. For environments with high-dimensional or continuous state and action spaces, Q-learning becomes computationally prohibitive or simply intractable. Policy gradients naturally extend to continuous actions by outputting parameters of a probability distribution. For instance, the mean and standard deviation for a Gaussian policy. This direct parameterization bypasses the need to discretize or search over infinite actions. However, this directness comes with a challenge. Policy gradient updates can exhibit high variance, making training unstable and slow. Techniques like generalized advantage estimation or trust region methods such as PPO, proximal policy optimization, mitigate this by carefully constraining policy updates, preventing catastrophic divergence. PPO has become a cornerstone, robustly scaling RL to complex tasks. Ultimately, policy gradient methods aren't just an alternative. They represent a fundamental shift in how we conceive of learning control, moving from an indirect value estimation problem to a direct behavioral optimization. They empower AI to develop sophisticated emergent strategies, pushing the boundaries of autonomous systems, not by telling them what to do, but by refining how they decide.